Hello, everyone. I am Yuwei from the University of Chinese Academy of Sciences. Today, I am glad to share my recent work, AFGEN, Whole Function Fuzzing for Applications and Libraries, which is going to be published in the 45th IEEE's Simpson on Security and Privacy. It's a joint work done by a group of researchers from the University of Chinese Academy of Sciences and the Ocean University of China. Fuzzing technology has been widely used in real-world applications and libraries. It mutates the input with little or no understanding of the details of the target program, and it needs to be improved for better program coverage. As more coverage achieved, more possibility to discover vulnerabilities. But it is challenging to achieve complete code coverage or program state coverage, and even the coarse grade coverage, such as the function level coverage, is hard to complete. Researchers proposed many works to explore the internal functions, the general fuzzing, such as the FL and FL++. They tend to cover more code, and the directive fuzzing, such as the FLGo, Parmesan, and Beacon. They generate inputs that target a set of specific code locations. The API fuzzing, such as the Fuge and Fuzzstring, they focus on the operations of APIs. However, because of the large number of functions and the complex dependency, they cannot achieve a complete function coverage. So, to solve this problem, we propose the whole function fuzzing. It fuzzes all functions directly by automatically fuzzing harness generation. And some functions are hard to trigger through application fuzzing, and LibFuzzer provides a method to test any function or program logic in the target program. We need to manually construct the fuzzing harness, which would divide and assign specific size of data generated by the fuzz engine to the functions. Then we compile and run the fuzzing harness until it triggers a crash. Since there are so many functions, we need the automatic fuzzing harness generation method, which generates the fuzzing harness for the target function by intelligently construct the code snippet. Currently, the automatic fuzzing harness generation methods are focused on the APIs because they have the detailed documents. Their arguments are basic or can be initialized by the specific functions, and compared to the inner functions, APIs have less dependencies. So, how can we extend the target of the automatic fuzzing harness generation from APIs to all functions? Take a simple case as an example. There is a function getByte in the ngFlip library. It reads one byte from the input union according to the mode flag. If it is set as a memory mode, the function reads a byte from an array. And if it is set as a file mode, the function reads a byte from the file. And the mode is determined during the compile process. If we want to build the fuzzing harness for this target function, we need firstly construct the proper program context, then assign valid values for the uninitialized variables, and finally make it satisfy the constraints of the program. For the context, we can slice the user's code of the target function, and for the arguments, we can assign values according to the variable types. By doing so, we now build a fuzzing harness which is ready to be fuzzed. And through this fuzzing harness, we can quickly trigger crash, which is a heap buffer overflow in line 14. Though both memory and file mode in the getByte function doesn't check the boundary, But this bug only exists in the memory mode, because in the file mode, which is the default mode, getByte calls the getC to read a byte from the file, which returns the end of file when there is no more data in the file. But this crash of the fuzzing harness doesn't mean there is a vulnerability in the project, because it lacks of the constraints. So we add the constraints according to a crash report of the previous fuzzing harness and rerun the new fuzzing harness. The crash still could be triggered, and now we can confirm that this is a real vulnerability. According to the motivation example, we know that to achieve the whole function fuzzing, we mainly face three challenges. We need to construct proper program context and to assign valid values for the uninitialized variables and satisfy program constraints to filter the false positives. To solve the above challenges, we propose AFGEN, which contains three main components. The bidirection slicer slices the usage code as a context. The variable value assignment assigns the uninitialized variables according to its type. And the constraints tracer traces the constraints according to a crash report and adds the constraints to a fuzzing harness to filter the false positives. The sliced code provides a basic context to fuzz target function. The bidirectional slicer locates the target function and adds the call statements and adds the statements that have data flow or control flow dependency and repeats the second step until no more statements with dependency found. We currently slice the function that directly calls the target function by default, as further slicing of high-level functions can lead to code size explosion, making it more difficult to fully test the target function. And we also apply some additional optimizations for slice code to improve the fuzzing performance. Developers usually output some variables to help debug program, which can adversely impact the fuzzing performance. Therefore, we identify such statements as harmless and eliminate them to simplify the sliced code and improve the fuzzing efficiency. And the sliced code could contain some syntax and logical errors, which break the correctness of the extracted code context of running the target function. Some control statements in the slice code may lack statements in their body. So we add statements within the body of these control statements to address this problem. And AFGEN assigns values to uninitialized variables according to their types. Here, we use three kinds of assignment methods to assign the value. The first is a basic assignment, which is targeting to a base type array pointer or the file handler. And the second is a combination assignment, which is targeting to the structure or the union type. And the third is a special assignment, which is targeting to the function pointer, cast pointer, enumeration, and the global variables. After applying the bidirectional slicer and the variable value assigner to a function, AFGEN can generate a compilable fuzzing harness. However, the fuzzing harness may not be complete and may result in some false positive crashes. So, we trace the constraints according to a crash report and add them back to the harness. To make the tracer more efficient, AFGEN only traces the constraints of variables directly related to the crash point, which are the variables in the statement where the crash occurs and the variables in the control statement. AFGEN locates the definitions of the given variables, applies state flow and control flow analysis for the variables, and records assignment statements and the control flow dependency variables are the constraints. The traced constraints cannot directly add back to the fuzzing harness. We need to adjust the variable names, remove new control variables, and skip variables initialized by the program input. Finally, we add the adjusted constraints back into the fuzzing harness and run it again to filter the false positives and confirm the real vulnerabilities. We evaluate the AFGEN in the three experiments. We firstly compare it with application fuzzers on 102 CVEs from 11 open source projects. Then we compare it with the API fuzzing tool on 5,292 functions. Finally, we compare the ability to discover new vulnerabilities. Compared to the general fuzzers, such as the FL and FL++, and the directed fuzzers AlphaGo, Parmesan, and Beacon, AFGEN can reproduce 66 CVEs, which is significantly more than other tools. An interesting finding is that the directed fuzzers did not perform as well as expected. AlphaGo only found 3 more vulnerabilities, even though it was given the extra information, such as the vulnerable code location. We also explore the reason of the performance of the fuzzers by checking the code coverage. The results shows that the AFGEN can reach more vulnerable code. And AFGEN can reproduce the CVEs more quickly. It reproduced the CVEs in the first hour, while the compare tools finished the reproduction after 4 hours. AFGEN can reproduce CVEs with more complexity in both code stack depths and branches. We list a number of branches and function nested depths in paths from the engine function to the vulnerable function. According to our analysis, the average numbers of branches and function nested depths of vulnerabilities found by AFGEN are 68.6 and 7.2 respectively. The performance of AFGEN is significantly better than FL++. We also verify the effectiveness of each component of AFGEN. By disabling one of them, the precision drops from the 7% to 47%. This shows that all three design choices play an important role in boosting the precision of AFGEN in discovering crashes. We compare AFGEN with the API fuzzing tool, Fuge. AFGEN can generate more precise fuzzing harnesses. For all functions, the precision is up to 77%, while the Fuge only achieves a 7.6 precision. We conducted an investigation into the AFGEN's false positives and discovered that most of them were caused by the inaccurate static analysis. We compare the ability to discover unknown vulnerabilities. AFGEN can discover 26 unknown vulnerabilities, and 24 of them are assigned with CVIDs, which is much more than the compare tools. Based on the method these vulnerabilities are triggered, we categorize them into 4 types. The general type refers to the vulnerabilities that can theoretically be triggered solely by mutating the input file and do not require additional options. The compile command means the vulnerabilities that require additional compilation options to be triggered. The API means the vulnerabilities that are triggered through API instead of the application's entry point. And the command option means the vulnerabilities that are triggered by specific command line options. In the end, to summarize our work, we propose whole function fuzzing to generate fuzzing harnesses for all functions of target programs. And we design and implement AFGEN with the slicer, the variable assigner, and the constraint tracer components. We evaluate AFGEN on the collected CVE dataset from 11 open source projects. It can generate more precision harness and reproduce 66 old CVEs and found 24 new CVEs. Thank you for your attention during my presentation. If you have any questions, you could contact me through the email.